Hi guys, how are you? I hope everything is well. Today we have a huge workshop. We have more than 200 slides. Don't worry, a lot of them are just animations and I hope we will be able to cover them today. If we happen to uh, if it happens to get too late or we don't manage to cover everything I have prepared, we're going to split the workshop. Don't worry, I'm going to make one more workshop for October. So if this one is going to be two parts, well, you're going to have three live sessions this month. Good, so before we start, I would like to say that my camera will be in the top right corner because we have a lot of animations like this here, and it will hide part of the images, part of the animation, so I prefer to have it up there. I'm not sure whether it will look great, but we don't have a choice. So what we are going to cover, we have to cover a lot. We have a lot of tree data structures. We're going to start with the basic ones, with the most, how to say it, the easiest trees out there, and we're going to uh, improve the difficulty one by one. We have more than three different types, more than 10 different types of trees to cover. And that's quite a lot. A lot of theory is going on here. The lecture is quite hard, but additionally, I've prepared a lot of code using the trees with a lot of tests, and I also added a skeleton which doesn't have the trees implemented. So the whole idea for this workshop is to listen about the tree theory, understand, try to understand whatever it's possible because it's quite difficult. Some of these trees are very advanced. Then try to go to the skeleton and implement the tasks yourself. If you happen to have a lot of trouble, if you run into issues, you can look at the provided solutions. So I am giving you a skeleton to exercise on and all the final solutions with all the tests passing. I'm not going to tell you all the trees we're going to cover because there are a lot. I'm going to just start. First, the lecture is super advanced. If you're not familiar with trees at all, if you're not familiar with data structures, if you're not familiar with math, it will be a little bit difficult, but don't worry. With time, everything will clear up. You may need to watch this lecture more than once. You may need to run through the presentation to see how the different parts of the trees work, how the different operations execute. So use the presentation as a hint how to implement all the structures. Of course, you may need to research a little bit, but the whole theory, the core theory is right here. Good, but make sure if you happen to like the lecture, if you happen to get yourself involved into data structures, try to complete the exercises. They're super important if you want to dive deeper in the topic. Also, I would like to mention that most of these trees are fundamental computer knowledge. If you go to advanced developer interview, most probably they are going to ask you questions about different trees, some algorithms over on them. They may uh, they may make you write a tree structure on a whiteboard. They may ask you how a certain algorithm works, and it's super basic and fundamental computer knowledge. This theory exists for decades. But in today's programming, where we happen to be just an average web developers. Typically, we use trees and we use data structures all the time, but we don't understand it. So consider this lecture as fundamentals how things work behind the scenes. For example, sorted dictionary and dictionary in the .NET world, they look the same. They have the same interface, they have the same methods. They look the same. They look exactly. Uh, if I'm not an advanced developer, I may never think that the implementation behind them is super different. For example, the basic dictionary of key value pair works with a hash table, but the sorted dictionary works with a red-black tree, which we're going to cover today. So the implementations are super different. And even though you're most probably not going to implement a dictionary by yourself, or you're not going to use a dictionary directly, you are using it every day. And it's a good knowledge to know how these things work behind the scenes, because the more you know about the code behind your code, you will be a better developer and you will understand why a certain part of your application is slow. You will understand when to introduce a different data structure and so on. So again, the lecture is advanced. Make sure you run over the whole presentation after 1-2 days after the video. Make sure you try the exercises at the end of the workshop, because they are uh, very interesting. The first time I tried to implement data structures by myself, it was super challenging and it was super rewarding when finally I was able to implement a priority queue, for example. So let's start. We're going to start with the tree-like data structures. And what's a tree? That's super basic. Most probably you already know that. Tree-like data structures are just branched recursive data structures. What does this mean? It means that these structures are not linear. For example, if we take a linked list or a normal list or an array or a hash set, everything is linear. You have one element after the first element, you have a second one, a third one, a fourth one, and so on. You have a sequence of elements. With tree-like data structures, this is not the case. Tree-like data structures have multiple elements after the previous one. So a typical tree data structure looks like this. And we have a node. A node is a place in which you can store values. For example, if you consider an array and you have cells which are numbered from 0 to whatever, and you can store values in them, in these cells. So the node of a tree is like a cell, but if we get an array, the first node or cell is always after the cell numbered 0. The second is always after the first. The third is always after the second. They're sequential, they are linear. With the tree data structures, that is a bit different, because each node may have multiple cells or nodes afterwards. So for example, this node has another node here and another node here and another node here. We are going to see all the different aspects of the tree in a minute, so I'm not going to give you a lot of details on this slide, but a tree data structure is not linear. You have multiple cells after the previous. And after these multiple cells, you may have even more cells. So it branches. If the normal array is sequential, A tree means that you may have another branch here and another here, and from here we may have another one, and that may be infinite. All the trees consist of nodes. A node is just a place to store your data. For example, this tree has numbers and it has 17, 9, 14 and so on. Each node can store multiple values, like for example an array of cats, and each cat has a name, an age and other properties. You may have a tree of cats. For example, this is a perfect data structure if you want to store your relatives. For example, if this is your grandfather, this may be your mother, this may be your her brother, and this may be their third sibling, for example. This may be you, this may be your sister, and so on. So uh, that's a good example of a tree data structure. The important part here is that each node is connected to other nodes. The connection may have directions, for example. They may be bidirectional, unidirectional, they may not have any directions. These connections may have additional values, but we are going to talk about that later. And there are many different tree data structures out there. Most of them look like this. Most of them look like this. We have a starting node at the top of the tree, and we have descendants, which often are called children. So these nodes here are children of the parent node above. I'm going to cover all the different definitions in tree data structures in 1 or 2 slides. So that's a tree, that's a binary tree. What's a binary tree? A binary tree means that every node has maximum of 2 children. Like here, this node has 1, 2 children. This node has 1, 2 children, and so on. We're going to see all the different algorithms in a binary tree as well. What are the typical examples of tree-like structures? First, the tree. The normal tree looks like this, and it has a root node. It has a starting node. That's the first node in the tree. From there, we have children connected to it, just like here. The main concept of a basic tree is that each node has at most one parent and 0 or many children. So the most important part here about the basic tree is that every single node has maximum one parent, or 0 if it's the root. This one, the parent, is the one above. This one, the parent, is the one above. This one, the parent, the one above. This one is the root and it doesn't have a parent. This one, again, one parent. This one parent. Each node has maximum of one parent. That's the important part of the basic tree. And each node has multiple children. It may not have any children. For example, the 8 here doesn't have any children below it, but it may have 3, 4, 5, 10 and more. So the first data structure is a tree, where each node has at most one parent. That's the important difference between a tree and a graph. A graph means that we have nodes, but there is no root, there is no starting point. For example, if you look at this picture right here, if you look at this tree's data structure, is there a starting node? No, you may say that this looks like a starting node, but if we take a look at here, there is no starting node at all. Nothing. We cannot dedicate a single root, a single starting node. And with the trees we can. They're always shown like this. The root node, the starting node, is at the top, and all the children are below them. Oh, their children are even below them, and so on. But with the graph, we don't have a root node, and each node may have multiple parents. For example, if we take a look at 21 here, we can see that it comes from 1, it comes from 7, it comes from 19. It's not that structured. It's more like a random data structure. So the graphs don't have any parents in their nodes. That's the difference between a tree and a graph. A tree always have a root, and each node has at most one parent. Graphs, they may have multiple parents. And there are, of course, different kinds of trees: binary, balanced, ordered, and so on. I'm going to show you the most common ones. And there are graphs. The types of graphs can be, there are a lot of types of graphs: directed, undirected, weighted, and so on. And the last tree-like data structure is a network. A network is a graph like this, but it has additional data on the connections. For example, like here. And what can be represented as a graph? The most typical, the most easy example is a city map. If we decide that this is, for example, our country, this may be one city, this may be another city, a third city, fourth city, and these are the roads between them. These numbers here are, for example, the kilometers between the cities. So these types of structures are used by Google Maps, for example. Google Maps use graphs to represent cities. The Facebook friendships are also graphs. Each person is a node, and each friendship is a connection. So, for example, if we have the following graph representing Facebook friendships, this person sent a request to this person. This person sent a request to this person. The fourth person sent a request to the 12th person, but he responded. So these two are friends, and so on. So there are a lot of applications of trees and graphs. The definitions for a tree-like data structure. First, the node. We already said what a node is. A node is like a cell in an array which stores some values. There's a connection which the official definition is called edge. So when I say edge, it means a connection between two nodes. And when I say a node, it's the place where we store our values in the data structure. So the node is the cell, and the edge is the connection between the different cells. We have a root, a parent, child, and a sibling. This is again part of the definition. The root is the first node in the tree. It's usually at the top when we represent the tree on an image, and it doesn't have a parent. Every tree has a single root. It starts from a single root, and from there all the connections start to span downwards. So we have a parent. The parent is, each node may have a parent, and usually it's visualized above the node. We have a child, which is the opposite of the parent. This node here has three children: this child, and this child, because they are below the parent. We have a sibling. The sibling means that if a node is on the same level like another node, it's a sibling. So if they have the same parent, they're on the same level. For example, 9 and 14 here are siblings because their parent is 17. 6 and 5 are also siblings because their parent is 9. Additionally, we have a depth and height. The height is the number of levels in a tree. So this tree has 3 levels, and the depth is how many connections you need to go if you start from the root to reach a certain node. For example, if we need to reach the node with 9, we need to have one connection. Starting from the root, we need to go there. If we want to go to 6, we have depth 2, because we need to go first to the 9, then to the 6. That means that we are on depth 2. A subtree means that if we separate part of our tree, it becomes a separate tree. If we kill this connection here, we now have a subtree with 9 as the root and 2 children, 6 and 5. So essentially we may have this as a tree, we may have this as a tree, we may have this as a tree. So all of these are just subtrees. Even a single node, if I only take this node, that's a subtree. It only contains one node. What's an internal node? Internal node is a node which has at least one child. So this is an internal node and this is an internal node. We have a leaf, and a leaf is a node without any children. In our case, these are 6, 5, 8, and 14. These are nodes without any children. So again, internal node is a node which has at least one child, for example 9, because 6 is its child, and a leaf is a node which doesn't have any children. It's at the end of the tree. It's at the last. We have ancestor and descendant, and these are just like the parent and the child, but it doesn't need to be directly connected. For example, 17 is an ancestor to 6, because with 2 connections we can reach it. And for example, 8 is a descendant of 17, because again we need 2 connections and we're going to reach it. The direction is always downwards. So for example, 8 is not a descendant of 6, because if we start from 8 we need to go upwards, and that's not correct. What are the common tree traversal algorithms? The common tree traversal algorithms are 2, because with a typical array or list or any linear data structure we can traverse it with a for loop or a for each loop, just by going one cell at a time. I'm going with the first, the second, the third, the fourth, and so on. But a tree is not sequential, and we cannot run a classic for loop to traverse it, because which node is at index 1? Is it this one? Is it this one? Is it this one? Or maybe this one? We don't know. We cannot use a classical linear approach to traverse the tree, but we may have the case where we need all the values from the tree, so we need to traverse the whole tree and extract the values. So with a typical for loop it won't happen. So basically traversing a tree means to visit each of its nodes exactly once. And the order of visiting the nodes may be different on the algorithm. For example, a simple algorithm may be, okay, enter a node, then get all its children, and then gets all of their children. So we may traverse the tree in the following manner. We start with 17, then we decide to traverse all the children. So we extract 17, then we extract 9, then we extract 14, then we extract 15. Then we say, okay, let's start with their children. So then we extract 6 and 5. This one doesn't have any children, so we skip it. And we continue with 15. So the last one to visit is 8. This is one way to traverse a tree. We may decide to go in a depth. For example, we may say, okay, start from 17 and go as low as possible. So go to 9, then go to 6, extract 6, and then start going backwards and try to find other children of the parent node. So extract 5. Then go backwards. Are there any more children in 9? No. So go backwards and go to the next child, extract 14, and so on. So we may have different algorithms to traverse a tree. The first and the most popular one is depth-first search, and the second, which is again super popular, is breadth-first search. Depth-first search means visit a node's successors first. So try to go as low as possible and then return back. I'm going to show you animations of these traversal algorithms in a minute. Breadth-first search means visit first the nearest nodes. Don't go as low as possible, visit the ones that are as close as possible. So the depth-first search algorithm is very easy to implement. Some function which receives a node says for each child of the node, run the same function. That's a typical recursion, and afterwards print node. What will happen with this algorithm is that we will start at 7, we will go to 19, we will go to 1. We will see that there are no more children, so we're not going to enter another recursion call, so we're going to extract 1. Then it will go to 12, then it will go to 31. Then it will be back to 19, and it will see that we no longer have any available nodes to visit. There are no more children. We visited them all. So it will print 19. Then it will go back, go to 21, and it will print 21. That's the depth-first search. So a short animation how depth-first search works. We start at the tree's root, at the root. Then we try to reach as low as possible, and we reach a point where a node doesn't have any children, so it prints 1. Then it returns back and tries to go as low as possible, and it sees 12, prints 12, and so on. So the whole algorithm will go like this. It will go to 19, it will see that it has multiple children, so it will go to 1. 1 doesn't have any children, so it will be printed. That will come back to 19, it will see 12, it will print 12. Back to 19, 31. Then it will go back to 19 again. It will see that no more children are available because we visited them all, and it will print 19. Then back to 7. Does 7 have any more children? Yes, of course, 21. So it will print 21 because below 21 there is nothing. It will return to 7. It will go to 14. Does 14 have any children? Yep. So it will go to them. It will print 23. And it will return to 14. It will print 6. Return to 14. Print 14. Return to 7. 7 doesn't have any more children, so print 7. Each algorithm will print the tree in a different way. For example, a depth-first search will print first the 1, and then will print 12 and then 31. It will print the lowest nodes first, but breadth-first search doesn't work this way. It will print the children first. Here it is. A breadth-first search is usually implemented by a queue, so the algorithm is something like this. We have a BFS with some node. We enqueue a node. While the queue is not empty, we extract a node, we print it, and for each child of that node in the queue, we enqueue it. And this will essentially print in a different way, because first we'll print 7, then the children of 19, which is 19, 21, 14, then their children, 1, 12, 31, and so on. So different algorithms produce different results. Of course, the same algorithm on the same tree will always produce the same result, but we may need to know what kind of algorithm we want to use. Do we want to traverse the tree first downwards, or do we want to first traverse the children? It depends on the situation. So BFS in action, we start with 7, we add it to the queue, we immediately dequeue it and print it, so we enqueue all its children, which are 19, 21 and 14. So currently in the queue we have 19, 21 and 14, and the output is currently 7. Then we're going to start dequeuing these numbers, and we're going to get 19. Then we're going to get these enqueued, 1, 12 and 31, and so on. So if we continue the algorithm, we will have 1, 12 and 31 in the queue, but then when we finish with these children here, we're going to extract a value which will be 21, this one. Then if we continue, we will see that 21 doesn't have any children, so we don't have to enqueue anything here. And then it will dequeue the next thing, which is 14. It will see that it has 23 and 6. It will add them to the queue, and so on. So the difference between these two algorithms are the depth first search will always print the lowest nodes first, so the root will be the last. And breadth first search always starts with the root and prints first its children, then their children, and so on. And different tasks require different algorithms. So these were the basic trees. A tree with a random number of nodes, with random numbers of children, but how is this useful? How a tree is useful? Well, the typical tree may not be that useful in a normal everyday developer's job, but there are different kind of trees which are more restrictive in terms of definition, and they are very helpful. For example, the binary tree. Let me see what's going on here. A binary tree A binary tree is the most widespread form of a tree data structure. And what's important about a binary tree is that it has at most two children, left and right. So the root is 17, it has 1, 2 children. The 9 has 1, 2 children. The 15 has only 1 children. So at most 2. We cannot have more than 2 children. We cannot have, for example, 3 or 4 or 5 or so on. This is the most widespread form, and we'll see in a minute why it's super efficient for searching, for example. How to traverse a binary tree? Well, we have a couple of options, and these options are named. The first option is pre-order. Pre-order means that we traverse first the route, then go left, and then go right. So we start with 17, then go left, 9, then go left again. Until we have a left option, we always choose the left option. So if we don't have a left option, then we go right. So go to 3, then no more left options, so we go back and go to 11. Then we go back and then go to the right of the route. So if we can, we go to the left. That's the rule. First the route, then the left, then right. Then we have an in order. First we go to the left, then we print the route, and then we go to the right. So if we decide to use this algorithm, the in order algorithm, which is super important, you will see later during the presentation. We start with 17, we go to the left, but don't print 17. We go to the left again and print 3, because there is no more left options. Then we print the parent of the tree, so 9, and then we go to the right. Then we go back. We completed the left part of the 17th, so we print the 17, and then we go to the right again. So the important part here is that we first go to the left, print the left part of the tree, then we print the parent of that subtree, and then we go to the right. That's an in order. And the post order means that we first go to the right, then to the left, and finally to the root. So we should find, we go here, left, right, root, sorry. We go here, so we print 3, then we print 11, and then we go back to the root. So these three types of traversal algorithms of a binary tree have different results, and the difference between the implementation is if we want to implement the preorder, we print different parts of the tree in different ways. For example, for preorder, we first print the current node value because we need to print the root first. Then we print the left, then the right. And with the in order, we print first the left, then the root, and the difference is only the order of printing and calling the recursion back there. Why the in order is so important? Because if we have a binary search tree, which we're going to cover later in the video, we will see that if we traverse it in post order, this is a perfect binary search tree. If we traverse it in post order, we will get the result sorted. Look at it. We have 3, 9, 11, 17, it's sorted. So this is a good way to sort or extract the values from a binary search tree in a sorted manner. We are going to cover the sorting later. We're going to cover what is a binary search tree in general, what kind of definitions it has. So the in order is very important because it keeps the tree in a sorted order if we want to traverse it that way. So let's introduce a binary search tree. So far we know what a tree is. A tree is a data structure which has nodes. Each node has multiple children, and each node has at most one parent. Then we introduce the concept of binary trees. Binary trees have at most 2 children. And now we introduce a binary search tree which have at most 2 children. Each node has at most 2 children, but also binary search trees have an order. For each node, elements in the left subtree are lower than the node, and elements in the right subtree are greater than the node. Look at it. This is a binary search tree. If you take a look at 17, all the values on the left are smaller than 17, 9, 3, 11. All the values to the right are bigger, 25, 20, 31. I don't know why this 2 is a little bit smaller, but never mind. It's still a binary search tree. So if we take a look at the 9, we have the left tree containing only lower elements, and the right tree of the 9, it contains bigger elements. So each node has on the left smaller values and on the right bigger values. And if we want to, for example, insert a value here, for example, if we want to insert the value 18, what we need to do to preserve the order of the binary search tree? Okay, is 18 bigger than 17? Yes, go right, because there are the bigger values. Is 18 bigger than 25? No, go left. Is 18 bigger than 12? No, go left. So attach 18 here as a child of 20. Then we want to add 5. Is 5 bigger than 17? No, go left. Is 5 bigger than 9? No, go left. Is 5 bigger than 3? Yes, go right. So we attach 5 here. And this way we preserve the binary search tree order. And if we traverse that in an in-order algorithm, which is go first to the left, then print the root, then go to the right, we're going to get all the values in a sorted manner. So, how to search in a binary search tree? Because binary search tree allows faster searching. Imagine the following. Imagine if you have the same values on an array. For example, we have 17, then we have 6, then we have 12, we have 25, and we have 19. I believe that's everything. 17, 6, 12, 25... well, I'm missing 9. Okay, so let's say that we want to search for the number 9 in this array, which is not sorted in any manner. To find 9, in the worst possible scenario, 9 is at the end of the array. So we need to make n operations to find 9 in the worst case scenario. We need to check this, check this, check this, check this, check this, and then we are going to find 9. So to find 9 here, we need 6 operations. We need, in the worst case, if 9 is at the end of the array, we need n operations. Which, if we consider an array with 1 million values, then it will be very slow. So with binary search trees, on every step we kill half of the tree. So if I want to search for 9, I just check, is 9 bigger or less or smaller than 17? Well, it's smaller, so the whole right tree is killed. We don't need to check there because we know that everything which is greater than 17 is on the right and 9 is not greater than 17. So we go to the left and we check whether the node is 9. Yep, so we return it. It's super fast to find elements in a binary search tree. That's why it's called search tree. So imagine that we're searching for 6. If we're searching for 6 in a huge array, the worst possible scenario is if that 6 is at the end of the array. With binary search trees, if the 6 is at the end of the tree, how it's here, on each step we kill half of the subtree. So is 6 less than 17? Yes, kill right. Go to the left. Is 9 greater than 6? Yes, go to the left, kill right. So we took only 2 steps to find the 6. And it's super efficient when the binary search tree is ordered, super efficient to find a value in it. How to insert a node? I already told you that. We start with, for example, 26, and we say, okay, is it bigger? Yes, go right. Is it bigger? Yes, go right. Is it bigger? Yes, save it here. Then we want to store, for example, 25.5. Is it bigger? Go right. Is it bigger? Yes, go right. Is it bigger? Yes, go right. Is it bigger? No, store it here, 25.5. So we have a strict order in which we insert values and a strict order in which we search for values. And the searching is super efficient. How to remove a node? So this is a little bit more trickier. To remove a node, what we need to do is, if node is no, exit. We didn't find the node. There is no node with this value. If node is a leaf, remove it. If node is non-leaf, we need to find replacement. For example, if we want to delete 9 and remove it, we need to find where to put 6. In this particular tree, it should be here. but we need to preserve the order of the tree. That's important. So we have three cases if the node is non-leaf. First, deleted item has no right child, like here. So we promote its left child. It's difficult to remember all of these. So if you decide to implement the data structures I'm showing here later in the code, you should look at the theory. It's not uh, it's not valuable to remember it. There is no point. You need to understand what the different data structures are, but that's it. And when you need to implement something, you just need to take a look at the theory, understand why it happens this way, and so on. So, for example, let's delete 9. If we want to delete 9, uh, if the deleted item doesn't have a right child, we promote the left one. We just promote it here and put the left one here. This is what will happen. Done. Still, the tree is in order. Then, if we try to delete and its right child, it has a right child, but it has no left child, we need to promote the right child. It's getting a little bit dizzy, but look at it. If we want to delete 19, what we need to do? We need to delete 19 and we need to promote some of these children to preserve the order of the tree. So if we promote 18, is 18 okay? It will be still valid. If then, do we want to promote 25? Will 25 be okay? Yes, it will be okay, but only if it doesn't have a child here. Because if it had, for example, here, let's say 21, what will happen if we remove 19 and want to promote 25 here? What will happen with 21? Because we need to have 18 and 21 on the left side of this node, which will not be possible because we are going to break the binary tree definition. So we can promote it only if the right child doesn't have a left. This is simple if check in the code, but we need to understand why it happens, because if it has a left child, we won't be able to preserve the structure of the tree, because imagine if we promote 25 and it had 21. So where to put 18 and where to put 21? Of course, we may decide to demote 18 below 21, but that means more operations. And we need to remove an item as efficiently as possible. So the third part is the deleted right child has a left child. So we need to delete 17. We need to delete the root. So what to promote? Should we promote 19 or should we promote 9? Well, what we need to do is find the minimum in deleted rights left. So we need to find the minimum in deleted right left. So if we delete 17, what we need to do is find the minimum on the rights left and promote that. And still we have a perfectly balanced, perfectly ordered binary search tree. Of course, you can promote different nodes with more operations, but these are the most efficient. You don't need to remember all of these specifics. You need to understand what a binary search tree is. You need to understand that while it removes an element, it needs to restore the order of the binary search tree. So what you need to do is find the most efficient way to promote and restore the order of the binary search tree. And this is the case. So somebody already did it for us and says if the deleted has no right child, promote its left child. So when we implement a binary search tree, we need to follow these rules. So what's the speed of insertion, search, and deletion? It's the height of the tree. That's the worst case scenario, because if we want to insert something, at the worst case we are going to insert it on the somewhere in the leaf. So 1 level, 2 level, 3 levels, and here. It's very efficient because on every step we kill half of the tree. On every step we kill half of the tree. Searching and deletion is the same. Now, we understand what a binary search tree is. Let's go to heaps and priority queues, because priority queues can be implemented with heaps, and heaps are just a binary tree. We're going to see how it's implemented. What's a priority queue as a data structure? A priority queue as a data structure retains a specific order of the elements. So it's like a normal queue. Imagine the following. We have a queue in a supermarket with some cashier here. So the first customer goes in, the cashier says, hey, sorry, but you need to wait 2-3 minutes because my computer is restarting, for example. So the first customer waits. The second customer comes here, a third customer, so a queue is formed. The first customer is going to be first because he is the first in line. That's a normal queue. But a priority queue is, for example, a pregnant lady approaches the queue and everyone sees that her belly is quite huge and says the following: hey lady, you can go before me. Hey lady, you can go before me. So the pregnant lady has a priority here to go first, even though she came last. Then, for example, a guy with a single bottle of beer comes, and everyone has a full shopping cart with a lot of items in there. And the guy just asks, hey, I just have a beer. Can I please go? Can I please move faster? And because he asked politely, everyone says, okay, sure. So go first. This is how priority changes. The priority queue is the same. We enter values in the queue, but it doesn't matter which entered first, like in the normal queue. It matters the priority. So in terms of numbers, for example, if we create a priority queue of numbers, we need to specify priority. For example, higher priority means will mean bigger values go first. So I push 1, then I push 10, then I push 3, then I push 5, then I push 15, then for example 12. And then I decide to extract a value. Instead of the normal queue way, extracting them the way they enter the queue, the priority kicks in and extracts the highest value, which is 15 currently. Then we decide to, okay, give me next. Then it will give 12. Then it will give 10, and so on, based on the priority. And if we decide to push later 20, when we decide to extract the next value, it will be 20 because that's the biggest value there. So if the priority is the bigger the value, the bigger the priority, then the priority will kick in and it will extract the biggest value. Now, of course, we need to do that priority thingy in a good and efficient way, because we cannot have 1 million elements, for example, and every time we want to extract the biggest value, for example, if it's 15, we need to search 1 million elements. That's not efficient. So the most important part here is to have an efficient way to store the priority. One of the ways to implement priority queues is with a heap. We're going to see what a heap is in a minute, and it's related to a tree. It's very compact and can be stored in a simple array. Priority queues need to have an insert, a pull, and peak. And we need to have a min or max. depends on the priority. If we have a max priority queue, then the biggest values will be pulled first. And if we have min priority queue, the smallest values will be removed first. So, what's the complexity goal? What we want to achieve here? If we have an unsorted array, inserting one value at the end of array is easy. If we want to pull something, it's not that easy. Because when we need to pull the biggest value, we need to search the whole array and extract it, which is kind of a slow operation. So it needs n elements and operations, if n is the length of the array, of course. A peak also costs us n operations, because in that array, if we need to get the number 5, we need to traverse the whole array. We cannot know in an unsorted array where the 5 is. There is, it may be the first element, but it may be the last. With a sorted array, it's easier, but the problem is that every time we insert a value, we need to resort it. So if I want to insert, for example, the number 4.5, I need to traverse everything to find where to insert it if the array is sorted. And if I want to insert, for example, the number 100, it will go to the final piece. So it's very slow to insert something in a sorted array. Yeah, pulling and picking is fast, because when we know that the array is sorted, the maximum value is always last, the minimum is always first. But the insert operation is not that fast. So what we want to achieve with the priority queue, we want to achieve logarithm of n, which is faster than traversing everything. And logarithm of n is exactly the binary search tree operations, because when we decide to search something, on each step we kill a lot of the values. On each step we kill a lot of the values. So the search operation here is logarithm of n. And that's the main idea behind the priority queue. We want to implement it this way so that we have logarithm of n on every insert, pull and pick as the worst case scenario. Because with an unsorted array, we saw that pulling and picking is slow, and with sorted array, inserting is slow. So here comes the heap. It will help us implement a priority queue. What's a heap? A heap is, again, a tree-based data structure which can be efficiently stored in an array. We are going to see in a minute how. So the heap has the following heap property for each node. It's a binary tree. We can see that it's a binary tree, but if we have a min heap, it means that the priority is for smaller numbers. The parent should be less than or equal than the children. That's the important part. So the parent needs to be less than its children. That's the rule here. You can see that this is not like a binary search tree, because we have a 6, and on the left we have a greater value. On the right we also have a greater value. So it's not like the binary search tree. It's still a binary tree, but it's not ordered in the way a binary search tree is. So everything on the left is not necessarily smaller than 6. But it's important to have this property. The parent needs to be smaller or equal than its children. So apparently 6 should be smaller than 8 or 10. If that property is satisfied, then the heap is satisfied too. Here again, 10 is smaller than 18 and 28. 18 is smaller than 22. We can see that each node is smaller than its children. That's the heaps property. If we have a minimum priority, of course. If we have a maximum priority, it will be the opposite. Each parent needs to be bigger than its children. So the binary heap means we have a binary tree and it follows the same principle. For example, this is a max heap, max binary heap, because it has at most 2 children, and each parent is bigger than the children. 5 is bigger than 4 and 2, 4 is bigger than 3 and 2, and so on. Every level except the last is filled. So when we fill a heap, we fill it in order. We fill it first this, then on to the left, then to the right, then to the left, then to the right, then to the left, then to the right. We fill it level by level. We don't care if the value is smaller. We just add children as necessary and then reorder the heap. That's the important part. So every time I want to add something to this heap, I will add it next in terms of the level. So I'm going to add a value. Is level 1 filled? Yep, it has all the children. Is level 4 filled? Well, I have 2 children here, but I can add 1 node here and 1 node here. Then I can add here, then here, and so on. So I add them one by one on the level. So every level on a heap is filled except the last one. The last one may not be filled. Then last is filled from left to right. So if I need to fill the next value, I'm going to fill it from left to right. I'm going to add it here because that level is still not finished. I'm going to add it here. Then add it here, then add it here, then add it here, and from left to right. So this is the binary heap idea, and the rule of the parent and the children, whether it's greater than or lesser than, still applies. But how? Because if I need to fill it this way, for example, if I need to fill 10, I'm going to fill 10, but 1 is not bigger than 10. What should I do? And there is an operation which I need to tell you about, which is heapify up. That's what it's called. Heapify up means find a place for this value here and change it. Go upwards and change values until the heap properties are satisfied. So what this means is 10 bigger than 1? Yep, exchange them. 1 should go there, 10 should go there. Is 10 bigger than 5? Yep, exchange it. 10 should go here and 5 should go here. And all of a sudden I have a valid heap. Because the 10 is the biggest element in my heap, it will come to the root. Then 5 is bigger than 1, so 5 is here. That's the heapify up operation. There is a heapify down, of course. But that's the idea. When I need to insert a new value to the heap, I find the level which is not filled, I add the value there, and then I exchange the values until the heap properties are satisfied. And the properties are the current value needs to be bigger than its children, when we're talking about a max heap, of course. So this binary heap tree can be very easily stored in array, because take a look at it. If we have a binary heap, we can draw it like this. This root here has 2 children. This has 2 children. This has 2 more children, and so on. If we draw it like this, we can see that we can store the values in an array, and extract some formulas to access the parent node or the child node. So the binary heap can be stored in a linear structure, and with formulas we can extract the parents from the linear structure. And here are the formulas. You don't need to remember them. When you decide to implement, for example, a binary heap, you just need to take a look at the formulas and use them. So if we have a parent, what's the formula for the parent? The current node minus 1 and then divided by 2. So for example, if we want to find the parent of the sixth element, which is this one, we need to say, okay, 6 minus 1, 5, divided by 2, 2. So we go to 2. And if we take a look at the heap, yep, that's satisfied. If we decide to check the 10th element here, we again 10 minus 1, 9 equals 4 when we divide it 2. So for the 10th element here, the parent is here, the 4th element. And the same thing is with the left child and the right child. If we want to access the left child of the current node, we just need to follow this formula. And when we need to access the right child, we need to follow this formula. And this way we can store the binary heap in the array. Very easy and very efficiently. Let me, because it's a lot of theory, I know, but let me show you, for example, a tree. A tree, we have a tree data structure, and we have a value in the current node, and we have children. And to store and use the tree, we can say something like this. Binary tree of string has this, which has a child binary tree and another child of binary tree, and so on. For example, a binary search tree, we can implement it with nodes. Here is a node. Each node has a value, a left and a right, which are initially null. The tree itself has a root, and then it just needs to implement the operations we saw based on the formulas in the theory. And how to use the binary search tree? We can say create a binary search tree of ints, insert values. It will store them in the order it needs as a binary search tree, and then we can easily find something in a range or a search. So the whole lecture has everything here as a code, but I suggest you try to implement the data structures yourself by using the skeleton first, and then take a look at the implementations. Of course, you can take a look for hints here and there, but it's very challenging to implement these structures, and it's very rewarding. You will improve a lot in terms of computer fundamental skills if you implement these. Good. Let's create a short 5-minute break, and I'm going to get back here. So let's continue with the heap insertion. What we need to do on every insertion, we need to insert at the end. For example, in this case it's here, and then we need to heapify the element. The heapify, it means we promote the element until the heap condition is satisfied, and the heap condition is parent to be less than the child, or the opposite, parent to be bigger than the child, depending on the type of the heap. So if we want to insert 16, we insert it here, and then we need to heapify it up. We need to promote it until it satisfies the conditions. So hop, now we need to change it. Now the 16 is completely okay with the heap condition. It's less than 17 and it's bigger than 15, so it's kind of okay. Then we need to insert 25. We insert it here because that's the next level we need to add it. For example, here, then here. This will be the order we are going to add elements. But on every addition, we need to heapify the element. So inserting 25 means, okay, check whether 25 is bigger than 6. Yes, it is, so change it. Check whether it's bigger than 9. Yes, it is, so change it. And until the heap property is satisfied, we do that. And now we have a perfectly ordered heap. When we delete something from the heap, what we want to do is we save the first element, because to delete something from the heap, it means to remove the element with the biggest priority. In this case, the biggest element is 25. So we want to delete it, and we want to reorder the other parts of the heap so that it still satisfies the properties. So the algorithm is, we save the first element because we need to return it to the client code which wants the element. Then we swap the first element with the last, and then we heapify the swapped one down until the condition is satisfied. So what we need to do is we pull 25, then we swap 25 with 6, remove it with the last element, and then we need to demote while the element is satisfying the condition of the heap. So what we need to do is demote it here, then demote it here. And that's how we return the biggest value and then satisfy all the heap conditions again. How to construct a heap from an array. For example, if we have the following array, we need to create a heap. So we need to change all the values in such an order to construct a valid heap. The whole idea here is that every subtree is heap with elements, and the idea is that the leaves don't need to be heapified because all of the elements will heapify down them. So what we need to do is we just need to get the array, find n divided by 2, and heapify down each element with the formulas, the same way we did earlier here, until the root element. So we need to start from 5 divided by 2, which is 2. We need to start from here and heapify this, and heapify this, and change the orders. This way we will get a heap constructed from an array of values. Here it is. Done. Then the second one, and it will be in a perfectly shaped condition. where priority queues are used, because the heap is essentially a priority queue, because we always know that on the zeroth element we have the most priority value. It's used in data compression, it's used in graph shortest paths or GPSs, it's used in pathfinding and AI in games, and in many other solutions. For example, when we have a graph, when we want to find the shortest path in a graph, for example, from one node to another node, we use priority queues. We use a heap to find it. The next data structure in terms of tree is a balanced binary search tree. So again, let's make a quick summary. We know what a tree is. A tree has nodes. Each node has at most one parent and many children, or zero children. Then we know a binary tree. Binary tree means we have a tree with at most two children on every node. We have a binary search tree, which means we have an order of these nodes. All the smaller ones are on the left and the bigger ones are on the right. That's the property of a binary search tree. It's ordered. And now let's see what's a balanced binary search tree, because we have an order but we don't have a balance. A binary search tree can be balanced. And what it means to have a balance, it means that subtrees hold nearly equal number of nodes. For example, this one. If we take a look at this subtree and this subtree, we have a nearly equal number of nodes, 3 here and 2 here. If we take a look at this tree and this tree, we have equal number of nodes, 1. Because imagine the following tree. If we have value here, then we insert the value and it goes to the left. Then we insert the value and it goes to the left. Then we insert the value and still it goes to the left. Then to the right. And then again to the left. This will not be balanced because the left part of the subtree below the root node will have 1, 2, 3, 5, 6 elements, and the right part doesn't have an element, 0. So in terms of a balance, this tree is not balanced because the left subtree has 6 elements and the right has 0. So subtrees are with nearly the same height, like this one. This subtree has a height of 2 and this subtree has a height of 2. They are the same. So for example, if I decide to add a value here and then a value here, I'm going to lose the balance node by node, because here I will have 4 levels and here I will have 2 levels. Of course, to balance the tree, I need to add a node here, then a node here. But what if the values don't match? Because I still need to follow the rules. All the smaller ones need to go to the left and all the bigger ones need to go to the right. And that's important. So I don't have a choice. If I want to add a smaller value, I need to go to the left, even though the balance may break. So a balanced search tree means that somehow when we add values, we need to rebalance the tree to make sure that subtrees have equal number of nodes and subtrees are with nearly the same height. Here is an example of a balanced binary search tree. It has all the properties of a binary search trees. All the left values are smaller than the parent. Here it is, here it is. All the right values are bigger than the parent. But of course we have a perfect balance here, because this subtree has how many nodes? 1, 2, 3, 4, 5, 6, 7. And this subtree has 1, 2, 3, 4, 5, 6. They're nearly the same. Also the levels, This has 3 levels and this one also has 3 levels. So it's important to have the balance, but how to do it? Because inserting, for example, if we have 33 and we start inserting values, 10 for example, it will go 15, 3, it will go here. Then we decide to add 11. It will go after the 10 to the right because it's bigger than 10. And this way we're going to start losing the balance. So how to balance it? Here come the AVL trees. AVL trees are self-balancing binary search trees. They will rebalance every time a tree starts going off balance. There's a kind of a cute visualization here, where if we try to add values to the tree, and if I purposely try to make it unbalanced, it will rebalance itself like this. Then if I add again a bigger value, I'm always adding bigger values. As you can see, I started with 10, 20, 30, 40. If I had a normal binary search tree, it should look 10 to the left, 20 to the left, to the right, sorry, 30 to the right, 40. Because all the values should go to the right because they are bigger. But this AVL tree rebalance itself every time it sees that the values are not balanced, like this. I'm going to add 60. It will add it, then it will go and it will rebalance the tree. And we can see that almost every time the tree has almost equal height, and it will never go with too much imbalance in it. I'm continuing to add big values to it, but it rebalances itself. Of course, there are formulas to rebalance the tree, and we're going to take a look at them. So the AVO tree is a binary search tree, the same thing, but it can rebalance itself every time it goes off balance. It has very good search, insert, and delete operations. It's super fast, and in terms of space, it takes as many nodes as it can, so it's n. The property of the AVO tree is that height of two subtrees can differ by at most 1. So this is a valid AVO tree, but if we add a value here, for example 1, it will need to rebalance itself so that the height will continue to be correct. How to do the rebalancing? So height difference is measured by the so-called balance factor. Balance factor of a tree is height of the left and height of the right. So for example, this one is 0 because it doesn't have left and right. This one is also 0. This one is also 0 because we have one height here and one height here, so 1 minus 1, 0. This one is 0 too because it doesn't have any children's, but this one should be 1 because on the left we have a 0, but on the right we have minus 1. So 0 minus minus 1 becomes 1. And the trick is to have a height difference of at most 1. When it becomes 2, the tree needs to rebalance itself. The range needs to be between minus 1 and 1. So this tree right here is balanced. If it becomes -2 or 2, we need to rebalance it. For example, when we hit 19 here, because 19 needs to go to the right, then to the left, then to the left again. So what happens is every time we insert a value, the tree will start calculating the balance factor with the following formula. And it will go up to the root to recalculate the balance factor, and then if it needs to rebalance itself, it will do it. How to restore balance, the tree performs rotations. We are going to see the rotations in a minute. So when we add 19, the balance here becomes 1. Then the balance here becomes 2 because we have a height of 2 here and a height of 0 here. So the balance should be 2. And this node needs rebalancing. Here we have -1 because we have height of 2 here and height of 3 here. 2 minus 3 minus 1. How to fix the imbalance of the tree? We need to perform rotations. Rotations are right or left. Here we have a right rotation. So if we need to rotate to the right, what we need to do is we need to set x to be child of y, and we need to set the right child of y to be the left child of x. So a right rotation will become like this. We need to rotate this node with the other node. You can see that y became the parent of x, and x now starts to be the right child, and this here connection becomes a left connection to the Higgs. That's the formula. So we need to set x to be the child of y and move the right child of y to be the left child of x. It's more difficult to say it than to visualize it, because rotating this just means that we need to move y on top of x. X becomes the right child, and we need to move the connection to the left. A left rotation is the same, but we need to move to the left. So left rotation will mean that we need to change that. And this is a rotation of x. So if we need to do a right rotation of x, we move y to be here, and x becomes the right child of y. Then to the left, the same thing. If we need to do a left rotation of y, we just move Higgs there and change the connection. Here it is. So when we want to insert something in an AVO tree, for example this one, we have the heights calculated. So what we need to do, we insert the value like in an orderly binary search tree. So if we, for example, need to insert 27, we go to the right, then we go to the right, then again we go to the right. Then we check the balance. So we calculate the new balance up to the root. Currently this will be 1, 2, 3, 4, and the tree is still balanced. If the balance factor is different than -1, 0, and 1, we need to perform rotations, either a left one or a right one. Here are some animations which will help you to understand what will happen. We have an AVO tree here. We insert 11. So we go to the left, we go to the left, we go to the right, we go to the right. Done. Now we need to calculate the height up to the root. Since we added a new node here, we need to update this value. So currently it starts to be 2, this needs to become 3, 4, 5. Now we see that the AVL tree now is imbalanced, because here we have 1, 2, 3, 4 levels, and here we have 2. 1, 2. So in terms of balance factor, this node is not correct because it will need to subtract 4 minus 2, it will equal 2. And 2 is not okay because 20 is 2. 20 is left heavy because it has more nodes to the left. So we need to perform a rotation, this kind of rotation. We need to perform it on the 20th node. So here it is. The rotation means move 12 up. So move 12 up. 20 needs to go down here. And we need to break this connection and change it like this. Just like we did in the right rotation 5 minutes ago. And the solution is right here. We can see that 12 went to 20, 20 went to the right, and the child here now becomes the child here, like this. And now the balance is restored. The AVO tree is completely balanced. Of course, we need to update the height of all of these moved elements. And now the balance is 0. It's completely okay. Good. But there's a one rotation problem, and it happens when the parent node have a positive balance and the child has a negative balance. Or the opposite. The parent node has a negative balance and the child has a positive balance. For example, like here. If we add 4, we will say that we have a -1 balance here and 2 balance here, because here we have 0, we have 1, so -1. For this node here, we have 2 and 0, then 2. So when we try to, we need to rotate that. But when we try to do a regular rotation, because of this, because the balance is not okay, it will happen like this. We add 4, we update the values, then we decide to rotate 5 because it's off balance, and it will become the following, which again is unbalanced because now the balance will be -2. Because when we move 3 here, move 5 here, and this one needs to change the connection because that's the rotation formula, and we can see that it's still off balance, so we didn't solve the problem. So how to solve it? We need to do double rotations. So we need to rotate right with negatively balanced left child. Left rotate 3, like this, double rotation. Boom. Then update the balance, and then rotate again, and now the tree is balanced. So in our code, when we decide to implement an AVO tree, we need to check for this condition. When a parent node have a positive balance and then the child has a negative, or vice versa, then we need to perform 2 rotations. First, we need to rotate 3, restore the balance, and then rotate 4, and it will be in a perfect form. When we update the balance, everything is restored. That's the AVO tree. The AVO tree adds a balance to the binary search tree. And every time we insert a value to the binary search tree, we try to or balance it by rotating nodes. B-trees. These kinds of trees I already mentioned in one of my previous videos on Patreon. I talked about database indexes because B-trees are super efficient to be stored on a hard drive. So the databases use B-trees to store the indexes of the columns. So B trees have an interesting concept because they're like a binary search tree, but can have more than one value in a node. And if we have a B tree of order B, the B tree has between B and double B keys in a node, and between B plus 1 and double B plus 1 child nodes. I'm sure you didn't understand anything, but we're going to see examples in a minute. I'm going to show it directly. So this is a B tree, and the most famous B trees are B trees of order 3. That means that uh, a B tree of order 3 must have at most 2 values in a node and at most 3 connections. This is known as 2-3 tree, and it's one of the more advanced trees, if I have to be honest. But it's still easier than the red-black tree. I believe the red-black tree is the most difficult to understand of the most common ones. So the B tree has maximum 2 values in a node and maximum 3 connections. The values are stored in an increasing order. And what's the rule here? What are the properties of this tree? So the B trees hold a range of child nodes, and they don't need a frequent rebalancing. They are not as the AVO trees because they're how to say, they're more balanced because of the option to store more than one value in a node. I already said that the database indexes are a good example of B trees, and they are perfectly balanced. So, a 2-3 search tree can contain the following: an empty node, a 2 node, which means that it has one value and 2 links to other nodes, to children, or a 3 node, which has 2 values and 3 links to other nodes. We're going to see them in a minute. So all items on the left are smaller and all items on the right are larger. It's the same as in binary search trees. So here it is. We have a node which has 2 values. What's interesting is that all the smaller values than 7 go to the left, all the bigger values than 11 go to the right, and all the values between 7 and the left and 11 go to the right, go to the middle. That's the important part here. If we have a 2 node means that it has only 2 connections and only one value stored here. This performs like a normal binary search tree. Everything to the left is smaller than 41 and everything to the right is bigger. But then we have a 3 node which has 3 connections. 3 connections means that all the values below 7 go here, all the values above 11 go here, and all the values between 7 and 11 go here, go to the middle. That's the property of the B tree. And it doesn't need rebalancing that much because we can store multiple values. This 2 node, which has one value or key and 2 links to other nodes, and this is a 3 node with 2 keys and 3 links. These are smaller than 7, larger than 11, and larger than 7 and smaller than 11. So essentially we have a range between 7 and 11 and it goes here. How to search in a B tree? Well, if we search for 12, we need to go to the left. Then we need to go to the right. We found it. because 12 is less than 13 and then it's bigger than 11. It's like a binary search tree. For example, if we search for 10, what we do for 10? 10, go to the left because it's smaller. It's not smaller than 7 and it's not bigger than 11, so we go to the middle. And now we search for a 10 here. Do we have a 10? No, so the value 10 does not belong to the B tree. If we search for 9, we're going to do the same. We search for 9, so we go to the left. 9 is between 7 and 11, so we go to the middle. And 9 is here, so we return it. That's how database indexes work. That's why they are faster, because the database doesn't need to search the whole table. It queues a lot of nodes during the traversal in the search. So how to insert something in a B tree of order 3? First, if we have a 2 node which has only one value, we add it to the 2 node and it becomes a 3 node. So we don't add a new node below the node, we add the value in the same node. So for example, if you go here and if we want to add 42, we can go here. No, let's add 33. So 33, it should be left, and we add 33 here. We don't add it to the right. That's the important difference here, because we can add it here. So how come some of the values are still single and they have nodes? How to do it? We'll see in a minute. So we add it to the same and it becomes a 3 node. What happens when we have a 3 node and we want to add a value? We add it here, but that's not a valid node because now we have 3 values. So that becomes a temporary 4 node, but it's not valid, so we need to change it a bit. And the temporary 4 node just becomes like this. So the middle value goes as parent to the other 2 values. The smaller goes to the left and the bigger goes to the right. So if we want to insert something into a 3 node, which parent is a 2 node, for example, insert 40, what we need to do, we insert 40 here, make a temporary node with 3 values, but that's not valid. So what we need to do is we need to move 40 to become a parent of these 2. But we already have a parent, so we combine them like this. So every time we need to add a value and it becomes bigger than 2 values in it, we extract that and move it as a parent. But since it already has a parent, we just join it. So 40 becomes next to 9, like this. What will happen if we already have values here? So if we want to add something here, for example 15, we need to promote it there and add it here. But then again we have 3 values, so we need to extract 30. So adding 25 will make the following: 30, 25 will go here, and 20 needs to be promoted. So it becomes 20, 30, 50, but again this is not a valid configuration of our node, so 30 will be extracted too. How to construct such a tree? We insert 50, done. The tree is empty, so adding 50 is easy. We insert 30, well, add it next to 50. We insert 35, sure, but 35 now should be added here between 30 and 50, but that's not a valid node, so we need to promote the middleman to a parent. Good, then we need to insert 20. We add it here and that's it. Then we need to insert 10. We add it here to the left, but we need to promote 20. and we attach it next to 35 because 35 is a single value. Done. Then from this we need to add 70. It's attached here and that's it, because that's a valid node, and the tree is good to go. Then we need to add 33. 33 goes here, everything is fine. We need to add 40, comes here, but this becomes an invalid node, so we need to promote 50. We promote 50, but 50 becomes invalid node next to 35 and 20. So what we need to do is promote the 35. And done. This way the tree grows much slower than a normal tree. As we can see, we already added a lot of values and we had like a lot of values and still only a height of 2. Typical properties of a B tree are they grow from the bottom. We saw that we add values and then promote parents, not the other way around as with the other trees. The number of links from the root to any known node, non-existent node, is the same. Transformations are local, only local. It's nearly perfectly balanced at all times, because inserting 10 nodes will result with height of a tree which is 2, and that's quite an improvement, because normal binary search tree can be 9 in the worst case is if everything is to the left, for example, which will be kind of a bad. So the performance, the binary search tree, in the worst case, search, insert and delete is n, and the average case is something like this. With the B tree, everything is logarithmic and the constant depends on the implementation. Next is red-black trees. Red-black trees are actually B trees but implemented as binary search trees, and red-black trees are maybe the most difficult to understand because we have rotations and we have color flippings. It becomes a bit crazy. Let's see what a red-black tree looks like. A red-black tree is representing tree nodes from a 2-tree tree with a left-leaning red node. So if we have 20 and 30 in a normal B tree, it will become 30 with a left child of 20, and the 20 will be red. I'm using purple here because red looks very ugly on the blue presentation, so this is a red node. So that will be the representation of a B tree here. Red-black trees are essentially B trees, but their representation is like a normal tree. We only mark some of the trees with colors, some of the nodes with colors. The sorted dictionary and the sorted set in the .NET world are implemented with red-black trees. What are the red-black tree properties? All leaves are black. So if a node doesn't have a child, it's black. The root is also black, always. No node has 2 red links connected to it. So if we have a red node, it shouldn't connect to a red node. Every path from a given node to its descendant leaf nodes contains the same number of black nodes. These are the properties. And red links lean left. That means that red links need to go to the left. We use rotations to correct the balance of the tree, and the balance, of course, is measured in height, depth, size, the same thing. So right sub-tree is here weights more, so we need to use a left rotation. A left rotation means to rotate the same rotation as before, but we need to swap the colors too. As we can see, if X was red, now Y is red. So when we rotate the values of the nodes, we need to swap the colors too. And this will preserve the in order. Right rotation is the same thing, but on the opposite side. So we rotate it like this and swap the colors too. So, but the red link now leans right, but this is temporary. We'll see in a minute. How to insert something in a red-black tree. We need to locate the node position. We create a new red node, add the new node to the tree, then balance the tree if needed. How to balance? Well, now we're going to see it. Inserting a single two nodes, because remember, a red-black tree is actually a B tree, so it has two nodes and three nodes, like the B tree. So if we want to insert a value, if it's smaller, we add a new red node here and add the value. If it's larger, we need to add it here, but the red node is leaning right, so we need to rotate it. And we do it like this. So every time we find a red node to be on the right, we need to rotate the parent. Here it is. We need to insert a smaller item at the bottom. So currently we have this tree. This is red. And the red node is leaning left when we add 50. Everything is fine. But when we need to add a larger item, for example 80, the red node is leaning right, which means we need to rotate it. So we need to get this and rotate it. And the value becomes like this. When we need to insert something into a tree node represented in a red-black tree, we have three cases. The element is smaller than both keys, the element is larger than both keys, and the element is between the two keys. So larger than both keys, what we need to do, we add the value, and then we flip the colors. But the important part here is that we need to remain the root black if that's the root. So if we add a value here and we have a red node on the left and we add the new red node to the right, we need to flip the colors. If we have a smaller like this, because we cannot have two values, two red values connected one to another, we need to rotate it. So we rotate it like this. And then flip the colors. It's very difficult to understand this. I know that. It has a lot of colors, rotations, and so on. This is the theory. If you are brave enough to implement a red-black tree, you just need to follow the rules. When you need to add something, you need to flip the colors, check whether it's a root, and so on. It's a bit tricky. And I think if you want to understand a red-black tree completely, you may need to rewatch this or take a look at the presentation step by step. Because a red-black tree, essentially this thing here, is a B tree like we saw earlier with 20 and 50. This is why when we do some insertions we need to change values, flip colors to make it the same as the B tree representation. So if we need to add something between 20 and 50, what we need to do is we need to add it between them. Then rebalance the thing and flip the colors. So we need to add 30 here. So we rotate 30, then rotate it again, and then flip the colors. Flipping the colors should change the parent color to red. But it's important to understand that if the parent is the root, it needs to be black. To keep the black root, nothing uh, nothing special. When we add values and flip the colors with the algorithms we saw, we just need to check if that's the root, make it black. That's it. Here is a more complete example. We need to insert 8. We insert 8 here because the usual, it's bigger, go to the right, go to the left, go to the left. Then we have the 8, but we have 2 red nodes, which is not correct. So we need to rebalance and rotate this. When we rotate it, we receive this. But then we have a leaning node to the right to be red. So what we do, we flip the colors. If we want to add something, let me check it. Again, we need to rebalance the tree. This is the overall insertion process. We have the following situation. From here, if we hit the following, we need to do a right rotation. If we hit the following, we need to do a left rotation. When we go to here, we need to flip the colors, and if the root is black, if this is the root, make it black. This should be the algorithm in the implementation. So we start from here. If we need to add to the right, we go here. If we need to add to the left, we move here and flip the colors, and if we need to add to the right, we move here. This is the whole process. And it's very tricky to implement that in the code. It's fun, and it's challenging, and it's tricky, and it's kind of difficult. The red-black tree has a good performance rate. The average case for searching is better than the binary search tree. The insertion is also better. And it's almost the same as 2-3 tree. It depends on the implementation, like we said. There are other types of trees, for example, AA tree. You may search it. It's called AA tree, which is easier than the red-black tree, and it's easier to implement, and it has a good performance too. Here it is compared to the AVL tree. We can see that the AVL tree is a bit better in terms of the worst case, but on the average case it's the same. Good. Now it's time for interval trees. Like I said, because a lot of animations, we already covered more than 70% of the whole presentation. So let's make a 5-minute break too, and I believe in 1 hour we're going to cover everything. It's a lot of theory, I know, it's a lot of stuff going on. After you watch the whole video, you may go through the presentation because it's made to be self-explanatory. You don't need to watch the video again. Of course, if you think you need, do it. But most of the time, you will be sufficient only with the presentation. Choose a tree and try to implement it. The implementation of the trees uh, are harder. They follow the order of the presentation. So implementing a binary tree is very easy compared to, for example, a red-black tree. Implementing a heap is easier than an AVO tree, and so on, because as you saw, we add a definition of tree, then we set what a binary tree is, only two child nodes. Then we added a heap, which is a binary tree with a simple rule. Then we had a search tree, which has an order. Then we have a balanced search tree, which has an order and rebalances itself. And finally, we added colors, and it became crazier. So I suggest you try implementing this one step at a time. Use the help of my solution and use the internet. Okay, so 5 minutes and I'll be back. Okay, so we need to continue with the interval trees. Interval trees are like a binary search tree but for intervals. They look like this. Every node contains an interval. It, for example, a range from 20 to 36, from 3 to 41, from 10 to 15. Otherwise, it's the same as a binary search tree. Just stores intervals, and it's very efficient for searching intervals. So if we want to find, for example, whether our tree contains an interval from 4 to 16, it's very easy just by following the formulas. It's very fast and very efficient for interval searching. Intersection of intervals means that if a.start is less than b.end and a.end is bigger than b.start, like this. These are overlapping intervals and non-overlapping. It should be obvious what a non-overlapping interval is. So the interval tree help us find all the overlapping intervals in a search. So elements in the tree are ordered by the start of the interval. So it's like a binary search tree. All the intervals that start with less than 20 go to the left. All the intervals that start with greater than 20 go to the right. So that way we can build the tree. Each node stores the subtree max endpoint. So for example, if we go here, it will store for this subtree the max interval. Here it's 41. Here it's 99. Here it's 99 because that's the biggest interval value we have. Here it's 1 because that's the biggest value on this subtree. Here is 15. So the tree is ordered by the minimum of the interval and it stores additional information of the maximum interval of the tree. How to search for any interval? For example, we want to search for interval from 12 to 19. So we start at the first node and we check if the left max is bigger than the start of the interval. So the left max is 15, we go to the left, otherwise we go to the right. The left max is 10, sorry. So we go here. Then if left max is not bigger than the start, we go to the right. So our interval currently is 12 to 19, so we need to go to the right. If the interval intersects, we return it. So the 12, 19 intersects with that, so we need to return it. Another example is when we search, for example, from 102 to 110. So we check whether the left max is bigger than the start. Currently it is, so we go to the right. Then we check and go to the right. We hit a no, so the interval is not in the tree. What we need to do to search for all intervals, we need to follow these formulas. For a given interval, we search all nodes to the left where x left max is bigger than start, and all nodes to the right where x right start is less to the end. And we will find all intersecting intervals. Here it is. As an example, we search for 950 and check 2036 intersects with 950, so we add it to the result. The formula says Higgs left max should be bigger than the start, so we go to the left. And we go to the left. If the interval here intersects, and currently it does, so we add it to the result. Higgs left max is not bigger than the start here, so we skip the left part. Because Higgs left max is 1 here, that value is 1, and it's not bigger than the start of the interval. So in this subtree, nothing intersects with our search. So we completely ignore it, and we skip the left and go to the right. Then we see that this one intersects with 950, so we go to the right. Add it to the result because it intersects, and this way we find all the intervals which intersects with the search from the tree. We just need to validate with the formula whether to go to the left and to the right. Otherwise, we traverse the whole tree. So on each node, we check with the formula if we should go to the left or if we should go to the right. In this way, the tree will be traversed, and all intervals which intersect with the search will be added to the result. But the efficient thing here is that on each node we can decide whether to go to the left or to the right. So for example, if we had more intervals here, which is not very possible because this is kind of a small interval, but if we had more here, and if we see that our search does not belong to this one, we can ignore all the values. So searching for all the intervals is very fast and very efficient, because we skip huge parts of the trees where the interval will not match. That's the whole idea behind the interval tree. It just stores intervals, it stores the maximum subtree values, and it stores the smaller intervals in terms of the minimum value to the left and the bigger to the right. And searching is quite fast. Next, a rope. A rope is again a tree, because everything in this lecture is a tree, and the rope is a balanced tree for indexed items which allow very fast insert and delete. It's very efficient for string operations where the string has a lot of symbols. It has a lot of characters. Typically, text editors, for example Notepad++, will use a data structure like a rope when the file is super huge. When we work with huge text files, the rope is the data structure we want to use because it allows us very fast insertions and deletions of the text. The rope is essentially a binary tree. It has two nodes. Each node has two children at most. And the leaf nodes contain a short string. Each leaf node contains a short string. And each non-leaf node has a weight value equal to the length of its string. You will see it in a minute. These structures are very efficient for super large strings. Otherwise, you should use either a list of characters or a string builder because they're better. For example, for 100,000 symbols, it's not worth to build a rope. But for huge texts with a lot of characters, then it's a good idea to create a rope. The rope has faster insert and delete operations at random position, because with string builders and lists, you know how a list operates. If we need to insert something here, we need to move this part of the list one step to the right. And with the ropes, that's not the case. But ropes have slower access by index position, because lists and string builders have super fast access. by index. The operation is super fast. So if we need to access characters in a string by index, the rope will not be our solution. But if we want to insert a lot of text or delete a lot of text at random positions, then it's super fast. Let's create a rope with an animation. Our string will be example of a rope. Usually a rope will have some split of characters. For example, 3, 4, 10. It doesn't matter actually. It depends on how we want to split the binary tree. But if we have an example of a rope, example split may be starting with the first 3 characters, then for example 3 or 4 and so on. So we add a node with our first strings, which is exa, part of the whole string. The node stores the substring value. It stores the length. So here we have 3 symbols, here we have 5 symbols. Mpo underscore, the underscore means space. I just added here because it won't be seen in the image. So when we see underscore, we mean space. It's easier to visualize. It's not a requirement by the rope to have an underscore. It's easier for visualization. So we add the first part, then add the second part, and then connect these two after we add, of course, some others. But the whole idea is that every time we add 2 values, we need to connect them to our binary tree, and the connection should store the left subtree height, which means 3 here. So every node contains the left subtree number of characters it contains. You will see it as we build it. Then we need to build these two. And the left subtree has 2. The split may come. The split depends on how we want to separate our text. In production ropes for huge files, usually the split has maximum 120, for example, characters. So this example uses a very small split because the string is small. But for huge texts, usually each node will have, for example, 100 characters. Good. So if we have these 4 nodes here, then we need to build the binary tree above them. Each node stores the length of the string, and each node which doesn't have a string stores the length of the left subtree. Here is 3 and here is 2. Then we add a parent node which stores the length of the left subtree, which is 3 plus 5, 8. Then we have another node which stores the whole string, which currently is 3 plus 5 plus 2 plus 8, 18. That's the rope. So we start by building our parts. We split the string, store the length of the string, 5 and 3, and then build up. We store the 3 because it contains the left subtree. Then we build the next one. Then when we have this, we build their parent, which contains the left subtree length, 3 plus 5, 8. And finally, we need to have a parent node, the root node, which contains the whole string. So how is this efficient and how is this good for large text? You will see in a minute. Here is how we can concat an example of a rope, our rope currently, here it is, and a second string which is concatenation. So we need to split the concatenation in terms of characters. Again, In a production rope, this should be, for example, 100, 112. It depends on, usually it's around 100. Then we need to build the second part of the tree, which is 4 here because we have 4 characters here, 9 here because the left subtree have 4 plus 5, and we need to connect that to 17 and add the whole string, which has 31 symbols. And this is how we connect a part of a string to another string. We just built the second part of the rope and connect it to a node. It's super fast. Here is how we can index a node. So if we want to find what's on index 12 in our string, we start from the root, we search for 12, so everything is to the left. Then 14, again we search for 12, we hit the 7, which is smaller than 12. What we need to do is subtract have 7 plus 12 and go to the right. So we now search for 5. Then again 5, we need to subtract 4, and then we go to the right, and when we find the 1, this will be the first index in this smaller string will be our 12th. Here it is. So again, if we want to search by index, we go to the left whenever the index is smaller than the node. We go to the right and subtract the value here and go to the right. And finally, when we reach a string, we have a value which we need to search in the string, and that's how we index in a rope. How to split at index 12? First, we need to find it by indexing, and then we need to cut it like this. So to split, we need to remove everything from this part and then remove the connections. And done. The rope is now split. Of course, we need to recalculate the values by going up to the rope, and we need to rebuild the second part of the rope. How to insert? This is where it's super fast. If we want to insert in A at index 12, we first need to locate it, and then we need to split. This is the split result. And to insert values, we just need to split the inserted values to nodes and build the rope about it. And then we need to connect it. That's how a rope works. Deletion is also super fast. We need to index, for example, 13, and we want a length of 12. We find the 13th index, we cut everything, and we find the second indexing, we cut everything there. We remove the connections. This is what we want to delete. And then we need to connect the other parts of the rope and recalculate the values. That's how a rope works. A rope is very difficult to implement, so I didn't include it in the skeleton. But the whole idea behind that is this. All of these buildings are a bit difficult to implement. The string splitting is also a bit difficult. Nevertheless, if you're interested in the rope, you can search it on the internet. But that's the basic idea how it's built. It's a binary tree which allows to delete, insert, and so on. How to connect it? Well, you find the first node which doesn't have a right child and connect it. Then build the second one containing the left subtree's values, and which is the whole string here. You build it, for example, 31, and then connect that to it, and then you build another node which contains the left substring like this. And the whole string length is at the root. What's a tree? Tree or tree. It's like a tree, but with a longer E, tree. A tree is a similar data structure. It's helpful for string searching, but it's very fast to search for prefixes, and you will see how easy it is to build. That's not a difficult data structure. It's easier than the rope. It's an ordered tree data structure, which is very, very fast for prefix searching, and you will see why it's fast. You can store a set of values with unique values where the keys are usually strings. You can do dictionaries, text searching, compression, a lot of stuff, but usually it's like a dictionary of key value pairs where you can search in the keys by a prefix. For example, if you have a phone book and you want to find all the Johns inside of it, you can search by Joe instead of a John, and it will be super fast to find everything which starts with Joe. So you will find Joe, John, and all the other names which start with JO. Here is how it's built. The root is empty. Then you want to add the word the tree becomes like this. Don't look the direction. It's very crooked, but it doesn't matter. It was easier to visualize it that way. So to add the word, you just need to add each of the symbols, each character in a separate node. THE, and this is the end. Then you want to add there. So what you need to do is the first letter is already contained in the tree. The second letter is already contained in the tree. The third letter is already contained in the tree. So you're going to need to build only R, and E. Done. Then we need to add these. So the first three are already added. So we have THE, then we need to add S and E. Okay, it was on the right side, doesn't matter. The direction doesn't matter. It's important to see that all the letters which the tree contain are not included. It just branches whenever it needs to add something else. When we need to add tree, it will add a T because it's already added, but it will add REE. Then tree, done. So everything, every symbol which is already added to the data structure will not be included. Rope, bam. There, bam. And searching is very fast because when you need to search for these, you can say, okay, I need R, which is not okay, then T, okay, I'm going from T. Then H, E, then I search for R, S, and then I will search for E. So the searching for prefix is very fast. Imagine if you want to get all the words in the data structure which start with D. So we need to get that, cut everything here, then you go here and extract everything from here. It's very easy to remove elements because you search by the prefix. Each end node, terminal node, may have a value, and this way you can build a dictionary. For example, you can build a dictionary of string to a cat. If we have an example of name age pairs, we may have Goshu with 24 here and Ivan with 18 here. And each set of key will construct a unique tree. So let's add Lucas with age 30. We add Lucas and store 30 at the terminal node. We add Lucia, age 18. So we add I and A and save the 18 here. Luigi 23, here it is. Warren 48, here it is. Wogan 23, here it is. Colin 5, here it is. Collie 15, here it is. Cole 32, here it is. When we want to search in that, we can say, okay, I want to get the everyone who starts with the letter L, and I want to get their ages. So the tree will fast remove everything here because it doesn't start with C, it starts with L, and include everything from this part of the tree. And we'll return Luigi 23, Lucas 30, Wusha 18, Warren 48, Wogan 23. It's super fast and efficient. It has very fast search by prefix, so it will be very easy and very efficiently to search just by part of the word and not the whole word. But it has a higher memory footprint. Other fast operations, add, contains, these are fast, and that's all. So, congratulations, we reached everything from the trees. These are the most commonly used trees. I'm sure if you haven't heard them or even if you don't know them, it will be a little bit of a mess in your head right now. Go again through the presentation. Look at the differences because each tree adds a feature on top of the previous one. And the ropes and the trees are kind of separate data structures. And if you are curious, check the AA tree. It's kind of an easy tree. Good, now let's take a look at graphs. But graph theory is huge, so we're going to cover the surface. If you're interested in algorithms which concern graphs, let me know and I'm going to make a workshop, a video, a tutorial, whatever. Just shoot me a message. So the graph data structure is like a tree, but we no longer have parents. Each node may be connected to every other node, and it's not that structured as a tree. We can see here that the graph has a lot of connections. They are kind of more random. A node doesn't have a strict parent. It can be connected to any other node. We no longer have the restriction to have a single parent at most. So a graph is denoted like this, and we have nodes V with many-to-many relationships between them. And these relationships are edges. Each node may have multiple parents and multiple children. Edges connect two nodes. So a graph may look like this. You can see that we have a self-connected node, a one-directional node, one-directional connection, bidirectional connection, and more one-directional connections. We have a node, an edge, node with multiple predecessors, and node with multiple successors. There's a self-relationship here. The definitions of a graph: we have a node, which is the element of the graph, may have a name, a value, and it keeps a list of all the nodes to which it's connected. We have an edge, which is a connection between two nodes. This may be directed or undirected. It may be weighted with some value or unweighted without any value. May have a name and value too. Some definitions for a graph. Directed graph is when edges have a direction, like this, like this. You can see that this part of the graph is not connected to any other part. That's completely okay. We have an undirected graph, where the edges are just connections, but it doesn't matter in which direction. We have a weighted graph. Weighted graph has a value, a weight or a cost associated to each edge. For example, if this was a city map, the city map, and these were some streets, and these were some parts of the city. These values here may be values in minutes to reach from point A to point F, or values in kilometers, or values in miles per hour, or whatever. It may mean something. A path in a graph means that we can go from one point to another. So ABC is a path, AJK is a path, AJNKJC is a path, but AHN is not a path, AHG is not a path, there is no connection here. A path is a collection of edges which connect to nodes. In directed graph, we need to take into account all the directions. So ABC is a path. AG is not a path because we cannot go from A to G, but we can go from A, B, and then to G. So that's a valid path, that's a not valid path. For example, from N we can go to K. From K we can go to nowhere because we cannot return. So there is no path which starts from K and ends in another node. We may have cycles, simple paths, and acyclic graphs. Cycle means that we start from one node and we return to that node. Like this, A, B, C, J, A. Simple path means a path which doesn't have any cycles. For example, N, J, K. Acyclic graph is graph without any cycles. If we have a graph with no cycles and no direction, we have trees, because if we take a look at the tree, we can see that it doesn't have directions and it doesn't have a cycle, because we can not go upwards in a tree. So we go down, down, and that's it. There are also other definitions. For example, connected graph means that every two nodes are reachable from each other. So if I start from here, I can reach every other node. But in this image here, if I start from here, I can reach only C and I cannot reach any other node. So a connected graph is this one. And this one is not a connected graph, but it has multiple connected components. A connected component is different parts of the graph which are connected. This one and these ones are two connected components. Where graphs are used, they have a lot of real-world applications. A computer network like the internet, for example, routes are simple paths in the network. City map, I already said that example. Streets are edges, crossings are vertices or nodes. Social networks, people are nodes and their connections are edges. Even the Facebook homepage contains a graph. State machines, states are nodes, transitions are edges. A lot of applications. For example, water pipes are a graph. You can think of a lot of real-world examples. How to represent graph in the code? First, adjacency list. Each node holds a list of its neighbors. If we have the following graph, we can have a list containing lists. So the first one contains the other. So the first one is connected to 2 and 4, so it will store 2 and 4. The second one is connected to 3 and so on. That's adjacency list. Adjacency matrix. Each cell keeps whether and how two nodes are connected. For example, with the graph here, we can go from the first node, we can go to the second and the fourth. So there is one here and one here. From the third node, we can go to the first. So if we go to the third node, we can see that we can only go to the first and no other. This is a matrix which describes the graph. It has a bigger memory footprint because we may have a lot of zeros in that array. And the last one is list of edges. So we just have a list which contains all the edges. 3, 1, 2, 3, 1, 4, 4, 2, and 1, 2. It doesn't matter which approach you choose, all of them are good enough. Depending on the task, you may decide to use one or another because it may be an easier. Here's an adjacency list of this graph. We have a list of int as an array and store all the connections. The 0 is connected to 3 and 4. The first is connected to 2, 3, 4, 5, 6. Here it is. 2, 3, 4, 5, and 6. The second is connected to 1, 4, and 5. Here it is. Second is connected to 1, 4, and 5, and so on. If you want to add an edge from 3 to 6, for example, from 3 to 6, we just say graph of 3 at 6. We can get all the children of node 1, which means all connections. We just get graph of 1. It's easy to represent graph like this. Here is the graph as adjacency matrix. The same thing. We store zeros whenever we don't have an edge, and ones if we have an edge. So node 0 is connected to 3. Here it is. So we put a 1. Node 0 is connected to 6, so we put a 1. If we want to add an edge, we say graph 3 of 6 equals 1. So 3 to 6, we just mark it as 1. If we want to get the children of node, we get it. We can specify list of edges. We may have an edge class, which parent and child. The parent and the child means we have a connection, one directional. Here it is, parent 0 to 3, 0 to 6, and so on. If we want to add an edge, 3 and 6, new edge, parent 3, 6. Searching is done through link. That's more of an object-oriented approach. We may also number graph nodes. This way we'll speed up working with graphs. For example, we may say Ruse equals 0, Plovdiv equals 6, Sofia equals 1, and so on. And this way it will be easier for us. Or if we know that these values are unique, we may use them as keys. So to number them, we just need to introduce some sort of a mapping in our code, for example, a dictionary of string to list of strings. This means that Sofia will have a list of all its connections. Sofia will have a list of Varna, Plovdiv, Burgas, Pleven, and Stara Zagor. That's the case here. Here is an example which is not sure how readable that is, but essentially this stores the graph in a dictionary of string to list. So This way we know that Sofia is connected to these cities, Plovdiv is connected to these cities, and so on. So this graph is represented in the code like this. If we have numbers, we may say a class graph which has a list of int child nodes and the node names. And we can say the node names are Rus, Sofia, Pleven, Varna, Burgas, and so on, and then mark them with numbers. There are numerous ways to represent a graph. And you can use an object-oriented approach. You can create a class node, class edge, or class connection, class graph, and other classes. A lot of options you may have. Or you can use an external graph, for example, quick graph, which is an old library, very mature. It has algorithms and a lot of stuff already implemented. How to traverse a graph? Well, depth first search or breadth first search works, but you need to mark nodes as visited, because when we have a graph like this one here, which has loops, which has directions, and if we want to visit all the nodes, we can no longer do the regular depth first search. We need to mark a node as visited. And the whole depth first search is, if the node is not visited, mark it as visited, and then find all its childs and print it. So if we want to visit all the nodes in the graph, we may mark it like this. Go to 1, mark it as visited, and for example, then go to 19, then to 7. Don't go to 1 because it's already visited. Go to 12, go to 31, go to 21, go to 14, go to 23, and then go to 6. So we just need to mark the nodes as visited. That's something which is important. Breadth first search is the same as the other algorithm. Again, it uses a queue, but it marks a node as visited. So if the node is not visited, we need to add it to the queue. Otherwise, we don't add it. That's the whole idea here. And again, it will go child by child, and it will not go in depth. First here, 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 then here, 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 and then this one and this one. That's the algorithm. There are a lot of graph algorithms which are very popular. We barely touched the surface. We just mentioned what is a graph and what's the main theory behind it. But we have a lot of algorithms. For example, connected components finds subgraphs. Topological sorting returns the graph in a sorted manner. It depends what sorted manner is, but still. A minimum spanning tree, which finds a tree in the graph. Dijkstra's algorithm, which is very famous and finds the shortest paths in a graph, from one node to all the others. Big connectivity finds articulation points in a graph. If you kill them, the graph is no longer connected, for example. Max flow algorithm, which finds a network flow in a graph, which is useful, for example, for water pipes. And A star, which is what the GPS systems are using. It has a pathfinding algorithm to a single destination. If you're interested in a workshop about these algorithms, I may do one. But of course we had a lot of trees here, so it was very intense. I couldn't involve a lot of algorithms because everyone who watches the video right now or during the recording will be super tired. How to combine data structures? Well, we need to know which data structures are fast for which operations. For example, stacks and queues are very fast for add and delete, but they don't have a find, they don't have a get by index, so they may not do the job. Static arrays have a slow add, a slow find, a slow delete, but very fast get by index. Double linked list, very fast add, but very slow everything else. Auto-resizable array, which is list of t, again very fast index, very fast add, but nothing else. Cache table, which is a dictionary, has very fast add, find and delete, but not get by index. Balanced tree based dictionary, which is a sorted dictionary actually. The sorted dictionary has a red black tree behind it. It's very fast for adding, finding and deleting. Hash table based set, it's very fast for everything but doesn't have an index, and so on. So combining data structures is when you have many scenarios but you don't have an ideal data structure for all these scenarios. So you should choose between space and time. You should choose whether to store more data structures and be more efficient in terms of time, or use one data structure and be slow. For example, we may combine a hash table for fast search, a hash table for fast search by two keys, name plus town for example, a balanced search tree for fast extract range, start key and key, a rope for fast access by index, a balanced search tree for fast access by sorted index. So different kinds of operations. You have an exercise in this workshop to try to implement a data structure which efficiently implements the following. We need to have an add operation, find, delete. The add adds a person by email, name, age and town. Find, you can find a person by email or delete a person by email, so emails are unique. You can find all which have an email domain, and you need to return the people sorted by emails. You can find all by name and town, and again you need to return them sorted by emails. You need to find all by start age and end age, again enumerable sorted by age. And you need to implement this as efficiently as possible. The solution is right here, person collection. You have the full solution. You have a lot of tests, unit tests, performance tests. You should try to find the perfect iPerson collection. Of course, in the skeleton, that's not implemented. If we go to the person collection and open the person collection class, we will see that nothing is implemented, and you will need to think of a way to implement it as efficiently as possible. Of course, the solution is right here if you want to check it out. So you need to implement everything by using lists first to make sure the logic works. It's not efficient, of course, but you need to validate the logic, run the tests to see that everything works, and then you need to start implementing efficient finding, efficient deletion, efficient find all, and so on. So that was it. It was a lot to grasp. It was a very long workshop actually, 3 hours. We covered a lot of trees. If this is the first time you see more advanced data structures, make sure you take a break 1-2 days from the lecture, then analyze again the whole presentation. It starts to get more difficult the more you read it. See everything and try to implement everything in the skeleton. I promise you it will be super challenging, but still, you need to implement a normal tree, a binary search tree, a heap, AVL tree, interval tree, red-black tree, and so on. So if you want to implement these data structures efficiently, try the skeleton, use the solution as your help, and hints. If you need any questions, you may ask them on Patreon as a message, on the Facebook group, wherever you like. So, for everyone who joined this live video, thank you guys. I hope you learned a lot because 200 slides are a lot to build. And have a great evening. Expect some news about the next live workshop. I'm going to publish now the extra video lesson for September, and I'm going to publish the posts during the next week. Good night for now, and sleep well.